All right, hope you guys are doing well. Last push towards tomorrow's AP exam. Let me start off just by going over just some items that I want to review with you and remind you, and then we'll get to the problems at hand. But at any point in time, if you have any questions that I'm not clear on, or questions that you guys have that I'm not addressing, feel free to you can ask by unmuting yourself, or you can put into the chat box. Okay, and I'll check that frequently so that I can answer your questions. Okay, so let's start off with this. Many of you guys hopefully have already started preparing for tomorrow. So first thing I want to kind of go over is making sure that you've gone through your exam demo, hopefully once or twice, where you're comfortable with the process, whether you're using your phone or whether you're using your tablet or whether you're using your laptop. Resources that I want to point out that I think will be good for you to print out. So the fall and spring summary sheet, derivative integral rules, calculator reference sheet, the exam day checklist. I think this is just for you to just make sure that you have everything in order. And then I have my tips and advice, which I went over in a video earlier, I think about Friday. So have those printed out. Also, I think FRQ assignments are good resources as well. If you have a chance tonight, look over them. Look over mock exams 1 and 2. I think between that and the ones I'm going to go over, I feel like derivative graph, Riemann sum, function table, differential equations, I feel like these are the ones that has the best chance of you seeing. Doesn't mean that these are the only topics that you're going to see, but I feel like they're going to try to work in these main topics. And I'll go over some of the other topics that they might stick in as well. And we'll get a chance to kind of see how they fit in over the course of this review session. I also included a couple of more for response questions, just more last minute problems if you have time that you want to do tonight. So that's for you there. And I will, I'm recording this session, so I'm going to put this up. I'll have a link to that after this session. Okay. Okay, final reminders for tomorrow. Make sure that you guys all have your e-tickets. Let me know if you're not able to find or see your e-ticket. It should be under your My AP account, or hopefully you guys all received emails from College Board. 10 sheets of paper with your AP ID initials and numbered 1 through 5. I just want to kind of model for you what that could look like. So I put these on half sheets. So obviously you're going to be doing this on full sheets here. So let's say for problem 1, you use all 5 sheets here, then it will be numbered 1 through 5. Okay. And let's say, and then you can also have for problem number 2, you also have your problems numbered here. Now, chances are you're going to use a lot less than 10 sheets of paper, but it's just nice to have it all set out and ready. So it just gives you one less thing to do when you're under time constraint. But also chances are that you're going to use a lot. You're probably going to use more for problem number 1, since this is the longer problem. So longer problems probably have more parts to it. And then, so let's say you only use 4 pages of paper, then you'll have just 1 through 4. And then for second problem, let's say you only did two pages of paper, then it'll be number 1 through 4, and then 1 and 2. Okay. All right. All right. So hopefully that's clear. Make sure your device is charged. Resources printed out or downloaded. We really want to try to avoid any internet searches. We just don't want to run that risk of being flagged. Okay. So just try to stay within whatever you printed out or what you've downloaded. Use blank printer paper instead of lined or graph paper. I think it's just easier for graders to read. and we don't want to have a chance of graders not being able to see your work clearly. So try to avoid line paper or graph paper, and try to use black ink as well. I think black ink is going to show up the best. Okay, let me include that as well. All right. Next is, let me see here. Next, so after the AP exam, which is after tomorrow, I'm going to be trying to enter in all your grades. I'm going to try to finalize all your grades in Infinite Campus. I hope to do all that by tomorrow sometime, but give me until Friday because Friday is when grades are due. But I hope to get it all done by tomorrow, Wednesday. So check Infinite Campus with your grades and make sure that you're seeing everything that it's supposed to be there. AP exam problems are going to be released 2 days after each AP exam. So I'm going to get a chance to be able to see it probably around Thursday, and then I'll try to work it out and put the solutions here for those of you who want to kind of see how you did or compare your answers. Okay. So if you entered into the exam using your e-ticket, and let's say you did use your e-ticket tomorrow and you experienced disruption, and you want to request a makeup exam, so I have a link here. So the link here at the bottom of the reminder page here, the assignment under schedules and reminder, I have the link for you to click on that. There's no phone number to call. The best you can do is if you wanted to do a retake, you're gonna have to click on this and you have to give your reason as to why you want to do a retake. And it's gonna be June 1st at 4 p.m. for that makeup exam. And you will hear from College Board on May 25th, okay? It'll be the Monday before your exam. Now, let's say you don't feel well tomorrow at 1 o'clock and you decide that even before you log in, you're not gonna take the exam and you wanna just take the makeup exam. Then there's nothing for you to do. College Board is gonna automatically send you that makeup e-ticket May 30th, that 2 days before your exam, so you don't have to do anything. But if you did log in, then you do have to do something. You do have to make sure you click on this link for approval. I've been seeing some issues that AP teachers are posting where students are having issues with submission of something, and that's just really unfortunate to hear. So I'm keeping my fingers crossed that you guys will all have a smooth experience tomorrow, and you're not getting any issues with submitting your responses. But we just hope for the best tomorrow. So yeah, I'm hearing some unfortunate things from the AP Physics tests, but hopefully now let's see. Yeah, so I do want to go over a little bit more about this. I think I have a page for that. So yeah, any questions so far? Okay, yeah. So the question here, so we should have a page for each problem. Not necessarily, okay, not necessarily. Let's say for problem 1, you did A and B, okay, and then halfway through B, you decided that you need more space. Then you can move on to page 2, and then you can continue. You can do B continued. Okay, and then you work this out, and then you do part C, and then you move on to part D here. So it doesn't matter if you don't have to fit all of part A or B within each page. The only thing is the restriction is 5 pages per problem. So College Board is only going to accept 5 photos per problem. Okay, but it's good to just have 10 pages ready, just in case you end up using all 10 pages. You have everything. You have your AP ID and your initials all set up and ready to go. So it's okay if you overlap into your problem, right? Just make sure that that they're in order, right? So you can do A, B, and then you can do B continued, and that's fine. Okay. But I think for the grader, it's probably best if you can fit all of, you know, part B under one page. But I don't think, yeah, that's not an issue. That's not an issue. Okay. Because the grader is going to have to see every, you know, a grader, when they grade your exam, they're going to read all of number 1 or all of number 2. They're not going to just read part A and then skip to part C. Okay, so it's okay as long as they're in order. Did that answer your question? Okay, so there was a question about whether we needed to have a page for each problem. All right, let's see here. Another reminder, extra credit due by tonight. So you have all these extra credit opportunities. I think mock exam 1 and 2 are the most important. If you're still deciding whether you want to do any or not, do these 2. I think these are the ones that I think could be most helpful for tomorrow and earn some points along the way. This is from Trevor Packer. I just got this message maybe a day ago. They're able to kind of keep track of what students are doing. So, you know, they've caught some students who are trying to develop plans to cheat. And so just as a reminder, it's not worth, you know, having your name reported to colleges, admission offices. So, so that's just a reminder there. Yeah, again, stay off internet searches, no communication with family members, relatives, friends, you know, Google Docs, just make sure that's not being shared with anyone, that everything is downloaded on your laptop or on your device. No online chat forums during the test, no social media. Okay, so just, just try to stay offline as much as possible, where you have everything downloaded on your laptop or you have everything printed out that you want to use. I think I went over this yesterday. Yeah, so just a couple of, I have, you know, steps for that. Okay, a question here is it okay to have a Google Drive open to download photos for us to upload? Yes, it's okay to have Google Drive open to download. In fact, I think that is the method that I would suggest, so they can easily transfer between your phone to your laptop. Just make sure that in your Google Drive that you don't have any shared files with anyone. I think that could be an issue, right? But if it's just your photo and you're moving it from one folder to the next, and then you're switching to your laptop to get that file, that's perfectly fine. Okay. Okay. All right. Any other questions with your AP exam demo experience or choosing between different methods? Yeah, make sure that your phone has, you know, this is for iPhone. So for iPhone, you want to make sure that that you're switched to most compatible. So you're always getting that JPEG format and not HEIC. Okay. Screenshots, make sure that you're double checking that your photos are clear, you're taking it overhead, you have plenty of light, double checking. Yeah. So just, you know, a lot of things to do, I know, but we want to just try to make sure that everything is, that we're able to submit something that where they're going to be able to read your work and be able to accept it. All right, so tomorrow when you log in, you'll log in using your e-ticket at 1:30. And in that 30 minutes, they're going to go through and go through completion for your identity information. So there's probably a bunch of things, a bunch of prompts that you're going to have to do. So you want to make sure you give yourself plenty of time. So 30 minutes at 1:30. So 1:30, you're going to log in. And then when 2 o'clock hits, you're going to see a timer for 30 minutes, okay? And then you're going to start working. All right. When you start working, you're just going to see 30 minutes. And when it goes down to 5 minutes, then you're going to start to then you're going to stop what you're doing. Okay, make sure that you stop what you're doing at 5 minutes or even a little before if possible, and start getting your responses ready for submission. What they also said is that it's possible that for some of the problems, there are more parts than what's able to be done within the allotted time. So don't try to squeeze anything past this 5 minutes. Okay, even if you're thinking, wait, I think I can get this down, I just need another minute or two. Don't take that risk. All right, just stop what you're doing at 25 minutes. Gives you enough time to take your picture. If you need to upload into Google Drive and be able to download it back on your laptop, you have plenty of time to do that. Okay, and also you want to double check, right? Each picture that you take may not be clear, so you want to make sure that you got to double check each of your photos as well. So you want to give yourself at least 5 minutes. Okay, when that experience is done, hopefully we all don't have any issues with submitting our response. Okay, and then it's possible that your files are still uploading in the background. If it is, it's fine. They'll move you on to question 2, and they won't show you 15 and 5. They'll just show you 20 minutes. Okay, so 20 minutes is going to start counting down. You'll see a timer for 20 minutes, and then you have 15 minutes to work on the problem. And when there's 5 minutes remaining, you're going to go through that same process. And when you get to the end, okay, look for this message. Your AP exam is complete. All right. So don't log out of your browser until you see this message. If it's taking a little bit longer to load, then just let it take its time. All right. You want to make sure you see this message. Okay. If you don't see this message, then there may be an issue, and you may want to consider doing the request makeup. But hopefully you guys all don't run into that issue. And when you do a request makeup, now what if, okay, so here is a possibility where you don't know if it took your work. And that is possible where you don't know whether it doesn't give you confirmation whether they've received it or not, and then you just don't know. And that is frustrating, I know, but if that's the case, then to be safe, go ahead and fill out your request makeup form and explain the situation, right? Explain the situation where I don't know if you've received my exam. If you did, then fine. But if you didn't, I want to make sure I'm in line to get approval for this makeup test. And so that's frustrating as well, I know, because then you're playing this waiting game. You don't know whether to continue studying and you have to wait till that May 25th date before they tell you whether you're approved or not. So, this is a bit of a worst case scenario, but, just want to kind of give you a heads up in case that happens, right? If you're not sure whether they received your exam, go ahead and fill out that request makeup and just explain your situation and let them know, I don't know if you received it. I didn't get a confirmation. So can you respond back to me? Can I get that confirmation? Okay. And obviously if they did, then you're fine. But if they didn't, then you want to make sure that you're in line, because they'll only allow request makeup form 2 days after your exam. So by Thursday, you need to make sure you have this in if you have any questions, if you have any doubts in your mind at all. Okay. All right. Any questions there? Okay, so the 4 topics I'm going to go over today are derivative graph, Riemann sum, function table, and differential equation. So these are the big 4 topics. But curve sketching, related rays, particle motion, limits continuity, implicit differentiation, second derivative, they may find their way into a sub part of one of these problems. Common theorems like IVT, mean value theorem, Rolle's EVT, second derivative test, L'Hopital's rule. So it's important that you guys get a chance, if you haven't already, go through the testing tips and advice, because these are these are some of the most common terms, common phrases, that catchphrases that College Board likes to use. So you want to make sure that as soon as you see those words, you know what to do. You know what to expect. You're kind of on top of, you're not looking at your notes and trying to figure things out, right? I think the idea of open notes is nice, but ultimately you have such limited amount of time, you're probably going to be working and putting stuff down on paper for your entirety of the time. So you really want to make sure you're really, really clear as to where your resources are. So if you don't know where things are, it's going to take some time, and to take away time from where you actually want to be working on the problem. Okay, so read through this. I would suggest that you go through the summary sheets as well. Highlight the portions that that you want to be reminded of. Okay. Let me see. Okay, maybe I'll go through this at the end. Okay, I don't want to take all this time before I get into the review here. Okay, so I'll set this off to the side. Linkage error and L'Hopital's rule. If I don't get to it, you guys can maybe remind me at the end. All right, so any questions with procedure? Any question with tomorrow? All right, let's take a look at number one. This is number one of the big four. Okay, so let's read the problem here. Let f be a differentiable function. So again, that just means a smooth curve. Now this is not the f function, right? You see a sharp turn here, but it's okay because this is not f, this is f prime. So our function f, which we don't see, okay, is differentiable, it's a smooth curve. It's defined on the interval from -5 to 6. The figure shows the graph of f prime. Graph of f prime has horizontal tangent at -3, so there's a slope 0 here. Area of the region between f prime and the x-axis is 5. So this is not a geometric shape. They're giving us what that value is. Okay. And we have piecewise linear functions here, different linear graphs that are just connected together. And the function satisfies f of -1 is equal to 3. Okay. So part A says find the absolute max and absolute min. So these are keywords, right? We see this on the closed interval, and we're just automatically thinking, okay, EVT, right? They're trying to get you to show the steps involved with extreme value theorem. So extreme value theorem means that we want to test the endpoints, and then we want to test the relative extrema. So we want to test endpoints and relative max and mins. So if we want to find, we know where the endpoints are, right? That's obvious. That's just -5 and 6. But if we want to find the relative max, relative min, we want to make sure we can pull those appropriately from the f prime graph. So as a reminder, anything above the x-axis represents where my original graph is going to be rising, right? Anything below the x-axis is where my original graph is going to be decreasing. Anything on the x-axis is where my original graph is going to have a slope of 0. So these are potential places where relative max, relative mins occur. So we can create a slope sine line. And our critical points are at -1 and at 2. And then we try to fill in our slope sine line, right? We see that this region is above the x-axis, so positive slope. This region is, all this is below the x-axis, so negative slope. And then from 2 to 6, positive slope. All right, so we see a relative max here, we see a relative min there, and these are both relative extremos, so we're going to test all 4 points. We're going to test find f of -5, find f of -1, find f of 2, and find f of 6. Now, there's no integral, there's no definite integral rule that tells us the location for f of x, so we're going to have to build it. Okay, so the way that we build it is we use this formula, right? We use this final position is equal to the initial position plus displacement. Or I can say f of b is equal to f of a, right? We have different variations of this. Okay. All the areas will tell us the change in position, but we have an anchor point. We have a starting point. So we want to make sure that whatever change in position we find, or the area between these regions, that we're making sure we're connecting it to our known location. Okay. So let's find f of -5 first. So f of -5, we're always going to start here. We're always going to start at our starting point, our given point. And then depth integral from -1 to -5. I know we're going backwards, but you want to make sure that when you start off your final position equals initial plus displacement, your lower bound is always going to have to be where your starting point is. Okay, and if it's upside down, if it's flipped, we can make that adjustment later. But initially, we want to make sure that this value is going to match this value always. Okay, so depth integral from -1 to -5. Okay, so now we take a step back and we see, okay, this is backwards. So, and I want to read the graph from left to right. So I'm going to flip those bounds. Okay, -1 I know is 3. I'm going to replace that with 3. I'm going to flip the bounds. Oops, -5 to -1. So now the from -5 to -1, we obviously can see that's just equal to 5. So 3 minus 5 is equal to -2. All right, so we have one endpoint found. Let's move on to the other point, f of -1. So f of -1, f of -1 is just 3, right? That's just given to us, so we don't have to do any further adjustment beyond that. F of 2, I'll box this here. F of 2, that's my starting point plus displacements. So this is equal to 3. And now we have to figure out what is the region from -1 to, sorry, from -1 to 2. So from -1 to 2, we see a triangle here. This triangle, we can do 1/2 base times height. So we have 1/2, 3 times -2. So that's -3. So we have -3 as our displacement. 3 minus 3 is 0. All right, one more point to go. We need to find f of 6 as well. All right, f of -1 is 3. And then the depth integral from -1 to 6. We have to find this region as well. So there's another triangle. We have 1/2 base times height. Okay, so that's equal to 8, right? We know this full region here is equal to 8. So we have 3 plus -3 plus 8. All right, so now we have everything that we need. We have our locations of our endpoints and our critical points, so then we compare. The highest y value that we see is 8. Our lowest y value, our minimum value is going to be -2. Okay, so we can write it out this way. Okay, absolute max is 8 at x equals 6, and absolute minimum is -2 at x equals -5. Okay, any questions there with part A? All right, part B, write the equation of the tangent of the line tangent to the graph at x equals 5. Use this tangent line to approximate f of 5.1. So we want to kind of make sure we let's see. Okay, want to make sure that we know our steps here for linear approximation. So for linear approximation, your first step is just trying to get that linear equation, right? Don't overcomplicate this. We're just going to find our tangent line equation. And once we have that, then we can plug that decimal into the x. So if I want to find my tangent line equation, I need to find my order pair and my slope. So we want to find f of x. So when f of x is equal to 5, all right, now with this f prime, so we have to find that through this process, this final position is equal to initial plus displacement. So we can do that process here. So f of -1, that's equal to 3. And then we need to total the region from -1 to 5. Now from -1 to 5, we see a -3 here, but to 5, notice that this is, maybe you're just thinking, well, maybe that's a trapezoid. This we can find, right, with 4, with a triangle 1/2 base times height. But we can avoid having to go through trapezoid if you do this. You know that this triangle is also 4, right? Total area 4, it's a mirror image of this one here, 1/2 base times height. And then you can figure out the area of this smaller region, right, which is 1. And if you know the large triangle is 4, the small triangle is 1, then 4 minus 1 is equal to 3. So we can figure out that region is 3. And now we can total our regions from -1 to 5. So from -1 to 5, it's going to be -3 plus 4, which is 1. 1 plus 3 is 4. Okay. So we have our order pair, which is at 5, 7. Okay. And then the slope is finding f prime of 5. Now, this is the f prime graph, so we can just figure out where that order pair is. F prime of 5 is equal to 2. All right, so we see that's the order pair, so that is going to represent the slope of our original function. We have our order pair, we have our slope, and now we put in the point slope form. Okay, once we have point slope form, let's get y by itself, and now we're ready for the approximation portion of the problem. So take 5.1, plug it in for x, and then use your calculator to reduce it down to a numeric value. Or you can leave it in this form. This is fine, or that's fine. Okay. All right, part C. Part C says, suppose g of x is equal to the definite integral from 3 to x of f prime. Find g of 3, find g prime of 3, find g double prime of 3. Okay. Now, if I want to find, let's see, tangent line in point slope form. Okay, the question is, do we need to leave the graph, the equation in point slope form? I would suggest point slope form. I think for this one, because it's asking for linear approximation, we're kind of moving it away from point slope form because we want to get that y by itself. But usually, if it's just asking for tangent line equation, this is perfectly appropriate. Okay, you don't have to do it in slope-intercept form. Remember, reduced expression is not going to get you any more points than unsimplified. Okay, so leaving in this form is fine. But we went a little further in this problem because we had to get y by itself. It's asking for that linear approximation for f of 5.1. But if it's just asking for a tangent line equation, then this is fine. Okay. But the reason why I like point slope form is because it's faster to get to than slope intercept form. And once you get to the most efficient way to your answer, then we can stop. Okay, so that's why I prefer point slope form. All right, part C, definite integral from 3 to x is defined as g of x. So if I want to find g of 3, I'm just going to plug this into my formula. So the definite integral from 3 to 3, note I haven't moved, right? If there's no movement and there's no error for me to find, that's just going to be equal to 0. Okay. The next step is finding g prime of 3. But to find g prime of 3, we first have to find g prime of x. To find g prime of x, we have to find the derivative of this expression. So the derivative of this expression is really the same thing as, I'm just going to write it out. I'm going to write out what I'm going to be doing. I'm going to find the derivative of this expression. And hopefully we recognize this as second theorem, right? If we're pairing two operations onto the same function and we know they're going to cancel each other out, we can just plug that upper bound into that expression, and there's our derivative. There's our cleaned up version. So once we have g prime is equal to f prime, we can just find g prime of 3, which is equal to f prime of 3, and f prime of 3 is just the order pair. So f prime of 3, this is my f prime graph, so f prime of 3 is equal to 2. The last step, find g double prime of 3. So before we can find g double prime of 3, we first have to find g double prime of x. So that means we have to find the derivative again. So g prime becomes g double prime, f prime becomes f double prime. So f double prime of 3 is just basically the slope of my f prime graph. So f double prime of 3, I need to not find the order pair, but to find the slope of this line. So the slope of this line, I can just go up 4 over 2, right? So up 4 over 2, that's a slope of 2. Okay. All right, any questions there with part C? All right, part D, evaluate the limit as x approaches 2 of f prime. Okay, so this is what I want to talk about. This is what I had on my sticky note here, is the way that we've been doing L'Hopital's rule may be an issue for College Board. So I want to just see if I can go through that with you. Whenever you see a messy limit problem, you're thinking, okay, it's probably going to be L'Hopital's rule, right? But we don't want to make that assumption. We want to go through the steps. Now, the way that I had us do it, and this is the way that the book had it as well, is, you know, we plug in, we see if it's a 0 over 0. If it's 0 over 0, we go through L'Hopital's rule. But this 0 over 0 may be problematic in terms of just an algebraic or numeric standpoint. So if possible, it doesn't mean that you're going to lose points for it. It's just it's possible that after I attend a webinar, they're saying that, you know, one of the graders are saying that this could be problematic. And so this is how we can be safe and still earn our points. Okay, so the way to be safe is you're going to find the derivative of, you're going to evaluate the numerator and evaluate the denominator. So you're going to plug that 2 in, okay? But you're going to do them separately, and you're never at any point, you're going to try to avoid writing it as 0 over 0. Okay, so this is how we do it. You're going to just evaluate the limit of the numerator. So don't do any derivative just yet. You're just going to do the numerator just by itself. So we plug 2 in, and we get f prime of 2. F prime of 2 is just the order pair, and that's just equal to 0. So we set that off to the side, okay? Separately, we're going to evaluate the limit of the denominator. So limit as x approaches 2 of e to the x minus 2 minus 1. Okay, plug 2 in. E to the 2 minus 2, that's e to the 0, which is 1. 1 minus 1 is 0. Okay, so in our heads, we're thinking 0 over 0. We know it's L'Hopital's rule, but we're not going to write it. Okay, we're just going to go from here and directly state, by L'Hopital's rule, my limit is going to be equal to the limit of the derivative of my numerator and denominator. Okay, so we don't write 0 over 0. We show the work to indicate that, yes, numerator and denominator are 0, but we're not putting 0 over 0. Now we're going to find the derivative. We're going to go through L'Hopital's rule. So the numerator, we find the derivative. F prime becomes F double prime. Denominator, we also find the derivative. The derivative for e to the u is e to the u times u prime. So e to the x minus 2 times x minus 2's derivative, which is 1. And then the minus 1 goes 0. So technically there's a minus 0. I left it out, but just want to show you where that -1 is going. It just goes away. Now, once you have your derivative variation of your limit problem, you're going to reevaluate. So plug 2 in for any remaining x's that you see. So that gives us f double prime of 2 over e to the 2 minus 2. F double prime of 2 is asking for the slope of the f prime graph at 2. So the slope of the f prime graph here, that's going to just be a slope of up 2 over 1, a slope of 2, right? That's a slope of 2 here. And then e to the 2 minus 2 is just e to the 0. Right? E to the 0 is 1. 1 times 1 is 1. So 2 over 1 is 2. Now we've gone through L'Hopital's rule, but our entire process, we've avoided this notation. All right, any questions with number 1? Okay, let's look at number 2. So the first one we looked at was a derivative graph. And then here, the second one is Riemann sums. All right, so let's read the problem here. A sand pit is being filled with sand whose height at any time t is given by a differentiable function, h of t. Again, we don't have information about h of t, but we do know that h of t is going to be a smooth curve, right? Differentiable function. Interval from 0 to 12. H prime is also a differentiable function. So even though we only see a couple of order pairs from H prime, we can rest assured that H prime is going to be a smooth curve all the way through. There's no sharp turns, there's no holes, there's no breaks. And H prime represents the rate at which the height of the sand pit is growing. So in inches per minute. So at 0 minute, the sand pit is rising at 1 inch per minute. At 1 minute, it's rising at 2 inches per minute, okay, so on and so forth. It is known that H prime is increasing on its entire domain. Okay, so this is a subtle but important point. H prime is increasing, okay? It's not the fact that H prime is positive, it's talking about the rate of change of H prime, so we'll come back to that. Values of H prime are given as select values. The height of the sand pile is 40 inches at t equals 9 minutes. So that's some information that I can kind of put off to the side. I know that H of 9 is equal to 40. Okay. At 9 minutes, the height of this sand pit is 40 inches. Estimate H double prime of 2. So we see the word estimation. We know that we don't have to go through calculus. We're just going to go through algebraic method. So H double prime of 2, we know H double prime is the rate of change of H prime. So we can just find the slope. So we want to choose the closest points. Now we don't see 2 showing up for t. So we just want to choose the 2 closest points. All right. So we want to just do change in height over, or change in rate over change in time. So H double prime of 2 is just equal to H prime of 3 minus H prime of 1 over 3 minus 1. So that's just 5 minus 2 over 3 minus 1. Now, this is the rate of change on top of this inches per minute. So we have to make sure we say inches per minute, which is really inches per minute squared. So what is the meaning of this number? So this is the fact that the sand pit height is increasing. Sorry, the rate of height is increasing at 3/2 inches per minute squared at t equals 2. So notice that this is a rate on top of a rate. So this is not the rate at which the height is changing. It's the rate at which it's telling us that the rate of height is increasing. Okay, so it's a rate on top of a rate. Part B. Use right-Riemann sum with subintervals given in the table to approximate the definite integral from 0 to 12 of h prime. Explain the meaning of definite integral from 0 to 12 of h prime in the context of this problem. So we're going to be accumulating these rates from one end to the next. So right-Riemann sum using the subintervals. So we can subtract the t-values to identify the width of each of these rectangles that we want to create. 3 minus 1 is 2, 9 minus 3 is 6, 12 minus 9 is 3. And it says right-Riemann sum, so we want to choose the right endpoint. So for each subinterval, you want to choose the height on the right. So 1 times 2, second subinterval, 2 times 5, third subinterval, 6 times 7, and then fourth subinterval, 3 times 10. Okay. So this, when we accumulate the h prime, it's no longer going to stay that unit, right? We're finding the area under this. So when we find the area, it's not going to stay as h prime anymore. So it was inches per minute, but now it's going to graduate to just 84 inches. Now this 84 inches doesn't represent, this doesn't represent how high the sandpit is. Okay, so I want to make sure that we understand this 84 inches represents the change from 0 to 12. So 84 inches is going to be the change in height of the sandpit in the 12 minutes. Now, if we want to find the total height of the sandpit, we'll have to add this 84 to whatever the height of the sandpit is at t equals 0. And that we don't know. Because we can work backwards from this h of 9, but we want to make sure that we understand this 84 inches doesn't represent the height, it's the change in height in the 12 minutes. Because here it's going to start off at some height, but then over the course, it's going to keep rising from that starting height, and it's going to increase by 84 inches. Okay, the question here is, instead of 4 subintervals, can we use 2? And the answer is we have to use 4. And the reason why is because it says with the subintervals given. So with the subintervals given, that means you have to use every subinterval that you can see. We can't create smaller subintervals than what you see in the table. So I know it looks like you can maybe do 2, but we have to use, because there are 5 order pairs here, we have to use 4 subintervals. Okay. All right, part D. Include units, evaluate the definite integral from 0 to 9 of h double prime. Now, if you look, we have nothing about h double prime, so we have to find a way to get this h double prime to convert into something that, where we have this, because we have limited amount of information, we have to find a way to connect these two. So what we can do though is we can clean this up, right? We can apply the definite integral on top of h double prime, and using first theorem, we know that the antiderivative is going to take a function and it's going to move it up 1 degree, or it's going to allow that function to increase from one derivative to the one higher. So that means we can apply this one and say h double prime, after the integral process, it's going to convert it to h prime, right? It's going to move it up 1. So it's going to turn to h prime, and then we can plug in our upper and lower bound, h prime of 9 minus h prime of 0. So now we have something that's usable, right? Now we have something that we can use. So h prime of 9 is just equal to 7. And then h prime of 0 is equal to 1. So we have 7 minus 1. That's equal to 6. This is another tangent line equation. I know we've seen this from the previous problem, but let's practice through this again. So write the equation of the line tangent to h of t at t equals 9. So we need to find order pair. We need to find slope. And then once we find our tangent line equation, then we can plug in this 10 to give it an approximation, or to find that approximation. All right, so let's see what information can we gather from this problem here. Okay, so what we can gather from this problem is h of 9 equals 40 because that's what's given to us at the beginning, okay? H prime of 9, right? What is h prime of 9? Is that given to us? Yes, so h prime of 9 is equal to 7. So we don't have to, we just have to go look for it. We don't have to do any calculations to find that out. So I can now create my tangent line equation. My y minus y1 equals m times x minus x1. But just so that I can kind of make this match the variables in the problem, this variable is t being the independent variable and h being the dependent. So I'm just going to use the variables in the problem. Instead of x and y, I'm going to use t and h. So I'll just let t represent what I would with x, and I'll let h represent what I would with y. Okay. So my order pair of T1 and H1 is just going to be 9 and 40, and then my m is going to be my slope. So there's my tangent line equation. Okay, I get h by itself because eventually I need to do an approximation, so I do need to kind of just do a little bit of cleanup, get that h variable by itself. And now we're ready for our approximation portion. Our approximation portion, we're just going to plug that 10 in for that t and see what number we get. 7 times 1 is 7 plus 40 is 47. Okay. So now the question is this number going to be an over approximation or under approximation? Because we're using a line to approximate this graph, right? We don't know what the graph of h looks like, but we just are just using a tangent line equation that's near that 10 and then just using it to approximate. So the question is, how can we figure out over approximation, under approximation if we don't know what the graph looks like? Well, we do have some information about h of t, okay? And this is the hint here. It says h prime is increasing, okay? It doesn't seem like something that is talking about h of t, but h prime is increasing. It's saying that the rate of change of the first derivative is positive. So we need to be able to look at this and be able to recognize this is really telling us that h double prime of t is always positive. So we need to be able to relate this with the words concave up. Now, let's see what that means. So the graph is concave up throughout the entire domain. It's not stating it, it's kind of giving us some hints, and we have to kind of make that jump ourselves. But if the graph is, if this graph of h of t, okay, let me label this h of t. I'm just giving us a visual here, right? H of t, this may not be what the graph looks like, but we know it's concave up, so I'm just going to graph a concave up graph, concave up shape. Wherever I draw my line, right? Doesn't matter if I draw a line here or if it's a tangent line to the curve, the line is always going to sit below the curve. And so any approximation that I use with my line that is part of a concave up graph is always going to under approximate. It's always going to under approximate. Okay, so this is an application of understanding how concavity and over approximation and under approximation works. Okay, now the flip side is, let's say it was always decreasing, right? If h prime is always decreasing, then we know that h double prime must be less than 0. If it's less than 0, then we know it's going to be concave down. And if the graph is concave down, then we can visually convince ourselves then that any linear approximation, any point on this line is going to sit above the curve and it's going to over approximate. So this is kind of a common popular type of problem that I can imagine test writers, just inserting it into one section, right? Especially with number one, where it's an extended problem, they can probably insert a lot of different types of, unrelated things, or not unrelated, but just, they can put in a lot of different concepts and just see what students know. Okay, any questions so far? All right, let's look at F and G here. The wording feels very similar, but we need to be able to convince ourselves if it's referencing a theorem that we can appropriately make that connection here. It says, explain why there must be a value C such that H prime of C is equal to 8. Here, maybe you're looking at this and thinking this is mean value theorem, right? We're trying to guarantee a slope given 2 points here, right? So maybe you're thinking, well, I know that this kind of looks like mean value theorem. All right, so this is mean value theorem here. But the problem is that we don't have any information with H of B and H of A, right? We don't have H of X to deal with. So we're not going to be having to deal with slope. This is the H prime graph. So we may not have to go through that complexity of mean value theorem because the information is given is everything is on that H prime graph. But what we do know is that the H prime graph is continuous, right? So let's just imagine these are the points for the graph that we're looking at. Can we guarantee an H prime of 8? Well, we see H prime of 1, or H prime value of 1, then 2, then 5, then 7, then 10. So it's going to have to cross 8 somewhere between 7 and 10, especially if we know it's continuous. So we have a different theorem for that. This is not calculus, but this kind of falls under one of the first theorems that we learned, is that if we're trying to guarantee a specific point and we know other points on the graph, and we can show that one point is below the target and the other is above the target, then, and we know it's continuous, it has to cross through at least one spot. Okay. So because we're looking at the interval from 9 to 12, and we're starting at H prime is 7 to H prime of t equals 10, then it has to cross through 8 at least once, right? Maybe multiple times, but because it's continuous, it has to cross through. So we can say, well, 7 is less than 8 and 10 is greater than 8. So between those 2 points, it has to cross through 8. Okay, so that's an application of IVT. Now, part G, explain why there must be a value such that H double prime is equal to 3/4. Now, maybe mean value theorem is more applicable because now we have H prime available and it's asking about H double prime. Okay. So initially, I wrote out what mean value theorem would be if I just converted F prime to H. But this is not what this is asking for, right? It's asking for H double prime. So I'm just going to take my mean value theorem and I'm just going to adapt it for this problem. So I'm going to say H double prime. So I'm going to take this, make it H double prime of C, and then these I'll make it H prime. So just adjusting it so that I can adapt it for my particular problem. So this is also mean value theorem, right? We can guarantee H double prime if there's a slope that exists on my H prime graph. So that's what we'll do. We'll take our endpoints, 0 and 12. We'll plug in A and B as 0 and 12, and see if we can convince ourselves that this slope between the endpoints gives us 3/4. So H prime of 12, we look at our table, that gives us 10. H prime of 0, we look at our table, that gives us 1. 10 minus 1 is 9. 9 over 12 is 3/4. So yes, we can guarantee this particular value because we're stepping through mean value theorem and we're told that H prime is differentiable, which also means that it's continuous. Okay. All right, any questions with number 2? All right, moving on to 3. So number 3 is table, function table. This the advantage of this for test writers is they can see whether students are able to do well with applications of product rule, of quotient rule, of chain rule, of U substitution. These are kind of good problems for them to kind of insert those topics in for students. Okay, the question from one of the students here is, do you think IVT will come up that often? If I had to guess, okay, if I had to guess, I would say that mean value theorem is a more important concept than IVT because there's actually calculus involved here. So IVT is more like, okay, does it, you know, it's just more like common sense, right? It's like, okay, if I start at a lower point and I end up at a higher point, then any point has to be reached in between. So I think this is a lesser concept. So if I had to guess, and there's only 2 FRQs, this is probably has a lesser chance of showing up. But I do want us to kind of notice that, you know, something that looks like that's kind of disguised as MVT is really IVT. So I want to kind of make us see that distinction between the 2 of them, so that you know, you have just more that you're more comfortable recognizing the difference when the wording is displayed as so similar. Okay. But yeah, but if I had to guess, this is going to be the higher priority. All right, so part A says g of x equals f of x quantity squared. I'm going to rewrite it using brackets so I can kind of visually see for myself. There's an inside and outside portion that I want to make sure I don't overlook. It says find the instantaneous rate of change of g. So we need to recognize this as basically saying find g prime of 9. Okay, we want to find the exact rate of change, the exact derivative, exact slope for the g graph. So I'm trying to find g prime of 9. Okay. So to find g prime of 9, we need to find g prime of x. To find g prime of x, we need to recognize this as chain rule. So chain rule means that we have to identify outside and inside portion so that we can fulfill the correct derivative here. So outside portion is the bracket squared. We'll do power rule there. And then the inside portion is the f of x. So we take turns with each derivative. Bracket squared becomes 2 bracket to the first power. And then the inside function from f becomes f prime. Okay? And we're always fill in our outer function with the original inside. Okay, so we don't want to do a derivative inside another derivative. We have to make sure we separate it into 2 distinct regions. Right, so now that we have our derivative spelled out, we can start putting in 9 in for x. So let's do that. Let's plug in 9 in for x. And we get 2 times f of 9 times f prime of 9. Right, I'm just making my substitution here. And then let's see what's f of 9. F of 9 is equal to -2. F prime of 9 is equal to -4. So we're just making substitutions, reading our table, and then getting it down to our numeric answer. All right. Next part here. Find the slope of the line tangent to the graph of k at x equals 3. So if I want to find the slope of the line tangent, I need to find the derivative. So I need to find k prime. So to find k prime, we need to recognize this as product rule, right? There's an expression multiplied by another expression, and I got to go through product rule, f prime g plus f g prime. Now we also need to recognize this as there's a hidden chain rule here, right? There's an inside portion with hiding inside that f of x. So we got to go through chain rule within this particular derivative. Okay, so there's my f prime g plus f g prime. Let's go through each part here. So what's the derivative of f of 3x? There's an outside and inside. So the outside is the f parentheses. So f parentheses becomes f prime parentheses. And then the 3x becomes 3. So this is the full derivative of my first term. Right, a little bit of chain rule here. The original g function, we just carry that down, no changes. original f function, carry that down, no changes. And now we're ready for g prime. So g prime, we need to find these this parentheses derivative. X squared becomes 2x, and 1 goes to 0. Okay, so now that's the hard part, right? The hard part is getting to the correct derivative, and now we just have to plug in and make sure that we can make the correct interpretation from function notation to numeric value. So next step, let's replace every x with 3. So I'm just going through and replace every x with 3. And now I just want to be able to pull the correct values. F prime of 9, again, is -4. F of 9 is -2. And now I'm just down to a bunch of numeric values. Use my calculator, enter that in. There's my k prime of 3. All right, part D, evaluate the definite integral from 0 to 3 of f double prime of 3x. Notice that we don't have double prime to work with, so we have to find a way to bring this up from f double prime to f prime, and then we can use this. But notice that there is that 3x there. We can't just do antiderivative just with first theorem. We got to keep track of that coefficient, so we got to go through use substitution. Okay, put a star next to this one. I feel like this is the way that graders are able to see if students can do use substitution without giving them a problem that they can just stick in the calculator. So I feel like this is a potentially good way for these graders to test students on their knowledge without a potential shortcut with the calculator. All right, so let's go through the steps here. We know we gotta go through your substitution. Our goal is this. Here's our goal. Our goal is to try to get this to look like this here. Because if I can get it into a nice clean variable inside, then we can push this through, make it f prime, and then we can evaluate our bounds, right? But we have to make sure that we don't lose track of the effects of that 3x. Okay, so the question is, can we use first fundamental theorem of calculus? And the answer is yes, okay? We're going to use first fundamental theorem of calculus, but before we get there, we got to resolve this 3x, okay? We got to go through use substitution before we can do first theorem of calculus, all right? Now, if this problem was just this, if this problem was just 0 to 3 of f double prime of x, then yes, then that would jump directly into the first theorem. There's no need to go through this use substitution, but that 3x is sticking out like a sore thumb. We gotta get this into the correct form before we do first theorem. Okay, so this is a way that graders can, or these test creators are able to see how students do with their use substitution. All right, so we let our u value be 3x. Derivative is 3. Solve for dx. Cross multiply, solve for dx, we get du over 3. All right, we make our substitutions here. Okay, so we're getting closer to the form that we want, right? I'm going to push that 1/3 out in front. Now, f double prime, right? Now we're in the clear. We know that f double prime is going to turn itself into f prime. So I'm going to have that 1/3 f prime of u, and then I'm going to start worrying about my bounds. Okay. Now, once you get to this point, you got to be careful because this is what a lot of students want to do. If they did the use substitution correctly, they want to do this. Okay. But do you see the issue with using the 3 and 0 with this expression here? Okay. There's a mismatch, right? The 0 and 3 are in terms of x. We went through use substitution, but we didn't make that adjustment with the bounds. So we want to make sure that we don't create a mismatch. We don't create a mismatch. So the way that we can avoid it, I think the fastest way to avoid it is, let's just bring that u back in terms of x. Right? Let's just bring that u back in terms of x. Because we found the antiderivative, right? We've done the calculus. Now let's just bring it back in terms of the original variable. And now we're in the clear to use the 3 and 0. All right. This is in terms of x. Our bounds are in terms of x. So now we can plug in. Okay. Replace the x with 3. We get 9 there. Replace the 0 and for the x, we get 0 there. And now if you look, we have information available, right? We have the f prime to use. So now f prime of 9 is -4. F prime of 0 is just -3. And that reduces down to -1/3. All right, so this is a way that they're able to test u substitution on the problem that's in function notation, because otherwise, if it's a normal problem that requires u substitution, students can just plug in the calculator and just get the answer. So this is a way that they're able to test u substitution and know that the calculator is not going to be able to help much. All right, any questions there? Next part here. Let n of x be defined as a definite integral from 0 to x squared of f prime. Find n of 3. So n of 3, this is the n of x equation, so we can just plug 3 directly in for the x. So let's do that first. So 0 to 9 of f prime, a definite integral from f prime. We don't have, well, we have f prime, but if we just found the area using the f prime information, then we're sitting at an approximation, right? Maybe you can use left Riemann sum or right Riemann sum or middle, but it's just an approximation. So we want to push this up to an f of x level, and that way we can get a exact value. So f prime becomes f of x. We plug in upper minus lower bound, and using our table of values, we get -2 minus 5, which is -7. So that takes care of n of 3. N prime of 3, now to get to n prime of 3, we first need to find n prime of x. To find n prime of x, I have to figure out the derivative of this mess. So the derivative of a definite integral, this is a reminder, you got to go through second fundamental theorem of calculus. Okay, so the way we do that, right, we know these two operations cancel each other out. The f prime is largely going to stay, but there's two things we got to take care of. We got to plug the upper bound into that variable, and then we have to make sure we also multiply it by the upper bound's derivative. So if it's just an x, it's not going to, there's no noticeable difference, it's just times 1. But this is more than an x, so the derivative of x squared is 2x. So we got to keep track of the fact that there's a little bit more with this derivative than previous because there's an x squared sitting here. So now that we have our formula for n prime, we can find n prime of 3. So replace the x with 3, we get f prime of 9 times 6. F prime of 9 is just -4. -4 times 6 is 24. Sorry, -24. All right, a couple more applications of chain rule here. It says let q of x be natural log of f of x. So the derivative of natural log of u, also find q prime of 5. Natural log of u is u prime over u. So our u prime is the f of x. So our u prime is going to be this f prime over f. Okay, so that's our derivative for this natural log function. So once we have f prime over f, then replace every x with 5, and then we just use our table of values. F prime of 5 is equal to 6. F of 5 is 4. We just pull that information from our table above, 3/2. All right, part K. R of x equals f of natural log of x. There's an outside portion. There's an inside portion. Outside portion is the f parentheses. The inside portion is the natural log of x. So we take terms with their derivatives and make sure that you don't combine it into one thing, that you're separating them into two distinct locations. F parentheses becomes F prime parentheses. Natural log of x becomes 1 over x. And now replace the, make sure you fill in the parentheses with the original inside function. And now we're ready to evaluate the derivative, but let's plug in, replace the x with 1. So we get f prime of natural log of 1. Natural log of 1 is 0. And f prime of 0, we have to look at our table, right? F prime of 0 is -3. -3 times -1 is just, sorry, -3 times 1 is just -3. All right, last one here, number 4. Okay, watermelon are beginning to come into season, and warehouse is receiving the watermelons over time. We have a strictly increasing twice differentiable function, so that just means a smooth curve. It's at least x squared or higher. Models the total number of watermelons in the warehouse when t is greater than or equal to 0 weeks, and our w is greater than or equal to 0. It is thought that w will satisfy the differential equation, okay, where w is measured in terms of watermelons and t is measured in weeks. At t equals 2, there are 10 watermelons in the warehouse. So write an equation for the tangent line. So yeah, so it's we see so many instances of tangent line equation. It's a good chance that it's going to show up on the AP exam. So tangent line equation requires order pair and slope. So our order pair we have here, right? 2 weeks, there are 10 watermelons. So we know instead of x and y, I'm going to use t and w. T is my independent variable and w is my dependent. So instead of x and y, I'm just going to do this problem in terms of x, t, and w. Use tangent line approximation to estimate the number of watermelons at t equals 3 weeks. Okay, so let's first figure out the point and the slope at 2 weeks. So our order pair is 210. So how can we find the slope? This is how we find the slope, right? This is the derivative equation. It's just another way of saying that's the slope formula. So we plug 2 and 10 in into our derivative formula. And in return, we get 4 times 1, which is 4. So we have our order pair, we have our point. And instead of y minus y1, I mean, you can. I'm just going to put it in terms of w just to kind of match the variables that I have here. So w minus 10 is equal to slope of 4 times t minus 2. Solve for w. And once I solve for w, I can use this to approximate the number of watermelons at 3 weeks. So we plug 3 in for t. 4 times 1 is 4. 4 plus 10 is 14. So we can approximate that there are 14 watermelons 3 weeks in. Okay, this next one here, let me work this out by hand, or let me work this out piece by piece with you. It says find d2w over dt2. This is asking for the second derivative. So this is our first derivative. So we want to find from first to second derivative. Now, instead of x and y, we're seeing t and w, all right? Instead of x and y, we're seeing t and w. So we have to recognize these still as 2 different variables, and we have to go through product rule. So I know this is a little strange. We're not used to seeing as many of these variables, but I do want to connect it with something that you do know, so that when I go through this, it doesn't feel as strange. Let's say the problem was this. Let's say the problem was dy over dx is equal to 2x times y minus 9. Okay, so I want to make this connection before I jump to this, right? So how would you do this, right? You do this the same way. You'll do product rule, right? So when we find the second derivative, we have to go through, we have to f prime times g plus f g prime. Okay, so this is more recognizable because I know we've done this a lot first semester. So let's go through our derivative, right? All right, what's 2x's derivative? 2x becomes 2. Okay, now here's the question. Oh, sorry, f and g, no changes there. So we have y minus 9 for g. We have 2x for f. Okay, so now the question is, what is g prime, right? What's g prime? We know that when we find the derivative for y, there's implicit going on here, right? So what do we say? We say dy over dx, right? 1 times dy dx minus 0. We found the derivative of my dependent variable with respect to my independent variable. So we get that dy dx. Okay, so we recognize this, right? We recognize this because it's x and y. We've been doing this for a long time. So I want to make that connection with this, right? So instead of x and y, we're doing t and w, but we're going to treat t like we would x, and we'll treat w the same way that we do with y's. Okay, so let's go through this. Okay, let me label the parts here. F prime times g plus f g prime. All right, 2t, the derivative for 2t is just 2, right? T is our independent variable. W minus 9, no changes. Back to f, no changes. So now the question is, what is the derivative of w minus 9? The derivative of w is 1, but we have to attach dw dt because this is the dependent variable. We treat w the same way that we do y. So just like how we have dy dx there, we're going to have dw dt here. All right, does that make sense? So I want to connect this with something that we do know how to do, and I want to make sure that we are understanding that this process that we're doing. Okay, so now that we have our second derivative equation, or some version of it, it's asking determine whether your approximation from part A, so part A, our approximation is 314. Is this an under approximation or over approximation? So what we're going to do is we're going to plug 314, okay, into our second derivative expression. So we'll plug 3 in for t. We'll plug 14 in for w. Now there's something that's sticking out here is what do we replace this dw dt with? So dw dt, we have to figure out what is dw dt at 314 because that's the order pair that we want. So we got to go back to this dw dt and plug in 314 so that we can make a clean substitution for this variable, here. So if I just take my dw dt, plug 314 in, I get 6 times 5, which is 30. So I have a substitution for that portion. Okay, everything else is just 3 and 14, but this dw dt I have to do a little bit more of plugging in. Okay, we clean this up and we get 190. So now we have to look, is this an over approximation or under approximation? Okay, so if we look at our w of t here, let's see. Yeah, so here we have a second derivative that is positive, right? So the second derivative is positive, we can conclude that must be concave up. If it's concave up, our graph looks like this. And if our graph looks like this, any line that we draw is going to sit below and therefore an under approximation. So it's that connection of using the second derivative and connecting that with under approximation versus over approximation. All right, part F, this is where we solve our differential equation. This is another popular topic that I would guess has a high chance of showing up tomorrow. So I'm going to go through this step by step. Let me transfer over to this page and just work off of this page here. All right, so we're going to solve this differential equation. That means we want to cross multiply. We want our w's on the left. We want our t's on the right. So first thing I'm going to do is I'm just going to cross multiply. I'm going to move that t over to the right side. Okay, move that t over. We don't quite get separation yet, but it's a little bit cleaner to look at when everything is up in the numerator. So now we decide, okay, what is out of place? What is not where they need to be? The 2t and dt looks like they're good to go. It's this w minus 9 that has to move over. So we'll divide both sides by w minus 9. So now we have integral of dw over w minus 9 is equal to the definite integral from 2t of 2t dt. All right, clean separation. So now we got to decide, all right, what's the appropriate antiderivative rule that we can do for both sides? This side's pretty straightforward. That's just power rule. This side, if it was w minus 9 raised to another power, like -2 or 3 or 1/2, then we got to bring it up. But either way, we got to go through u substitution, right? So u substitution, let's get those in terms of u. We'll let our u value be w minus 9. So du over dw is equal to 1. dw is equal to du. This is going to line up nicely with a natural log problem, or 1 over u du. This is just going to become natural log of u. 2t, we go through power rule. Let's bring the u back in terms of x, back in terms of the original variable here, so w minus 9. Reduce a little bit here. So I've taken care of the calculus. So now I just have to figure out, I'm trying to find my specific solution. So I'm going to take my order pair and plug in, right? I'm going to find the C value using my order pair of 210. Okay, so 2 plugs in for T, 10 plugs in for W. Natural log of 1 is just going to be 0. So C is equal to -4. Once we find our C value, we're going to put it back where we initially made that substitution. And then the rest is just algebraically trying to get that W by itself. All right, good so far. All right, so now we have our C resolved. We just have to find a way to get that W by itself. W is stuck inside the natural log. So the way we can release that W away from natural log is, let's just exponentiate both sides with base E. This cleans up nicely to be just absolute value of W minus 9. We're going to drop the absolute value, but when we drop the absolute value, we know that there's a plus or minus that's going to result on the right side. And then we'll add the 9 over. So now we have to understand these are two separate solutions. You got a positive e to the t squared minus 4 plus 9, and you have a negative e to the t squared minus 4 plus 9. So then we have to make a decision, right? Which one do we choose? And the way that we know which one to choose is you look at your order pair and you look at the y value. Whatever the sign of the y value is the sign that you want for your equation. Okay? You only have to do that if you're deciding between a plus or minus. This shows up if we do the square root of both sides, you end up with a positive negative square root. So we see that that's a positive 10. So that's going to help us narrow down to the fact that it must be the positive e to the t squared minus 4 plus 9. All right, any questions there? So I think part G is pretty straightforward. It's just asking, well, we have W of t. What is W of 0? So we can just plug 0 in for t. And what does that represent? So W of 0 just represent how many watermelons there are at t equals 0 weeks. All right, any questions there? Okay, so the question here. Yeah, the question is, if the ordered pair was 2, -10, if it was 2, -10, then our answer is going to be W is equal to negative e to the t squared minus 4 plus 9. Yeah, if our ordered pair was negative, right? Yeah, so negative sign is going to translate to a negative. But you only do that if you have a decision to make, right? So not every differential equation is going to, you're going to need to make that decision. But if you see that you got to resolve the absolute value and there's a plus or minus that shows up on the right side, then you can do that. Caitlin asked, do you think related rates will be on the exam? So it's a good question. This is what I'll say. I will say that I don't believe related rates will be the overall structure of the problem. I feel like there are bigger topics like differential equation and derivative graph and Riemann sums. But this is what I will say. I will say, though, that I can see them inserting a small related rates problem into like a portion. So I'm glad you brought that up because I do. So let me show this to you here. This goes back to that sandpit problem. And this is one part that I didn't put on and I realized because I didn't have room, but I'm glad you brought that up, Caitlin. So this is what we're going to do. Okay, let's look at this problem here. There's a sandpit problem that we did for number 2, and let's say part I says suppose the volume of the sand is given by V is equal to 10H. Find the rate of change of the volume of the sand with respect to time. So notice that anytime you see any respect to time problems, and you're given an equation, that's a hint that we got to do related rates. Okay, so let me go through this here. We're going to do related rates for this portion here. So related rates for this means that every variable is going to be attaching its own derivative variable. So v becomes 1 dv dt. 10 is a coefficient that stays. H goes to 1, but it also produces its own d over dt because of time. And now we look to see what we can fill this in with, right? So let's find the rate of change of the volume with respect to time at t equals 3 seconds. dH over dt at 3, right? dH over dt at 3 is 5, right? It's basically, dH dt is basically the same thing as h prime. H prime of 3 is 5. So we can make that substitution there. And that's just going to be equal to 50. And then our units of measure, right? This is dV, so that's the rate of change with respect to time, volume with respect to time. So we're talking about height in terms of inches. So it's going to be cubic inches per minute. So that's what I'll say. I will say that I can see them inserting like a small little related rates problem into one of these larger formats. But I don't think you're going to see a fully extended related rates problem. Okay. Okay, any other questions? There is one thing I want to go over here. And I brought this up in the advice and tips Zoom session. But again, I want to kind of go over this. Maybe this is not going to be a big deal. If anything, it's like 1 point. But this, or losing 1 point. This is an example of linkage error. So linkage error is where students use equal signs sometimes to just show that they're progressing from one part to the next. Right, and sometimes students may not be thinking exactly the effects of the equal sign, and so a lot of times students put equal signs all over the place. But sometimes College Board looks at those equal sign and looks at it really carefully to decide, wait, is what when you put equal sign, are you really showing, are you really indicating that the two parts are equal? So here's an example of that, where a student may just use equal sign in a way to kind of progress the problem along, but really they're making a potential mistake here. So for instance, let's say the problem gives you this this known, okay, this given, and then the problem is asking you to find the depth integral of 1 to 4 of f of x of 1 times 1/3. This is pretty straightforward. You just plug that 6 in for the integral and times that 1/3 and get our answer. But as students are doing this, maybe they're working out this portion and they're just putting equal sign because they just want to kind of move the problem along. And then and eventually it's correct, right? It's equal to 2, 6 times 1/3 is 2. But there's a linkage error here because this 6 is not truly equal to this definite integral. And so they may take a point off there. And so that's kind of frustrating because sometimes I've graded AP exams where I got to take off a point because even though they did everything right, but there's this equal sign that's causing there to be an issue. So what you can do to avoid linkage error is use arrows. If you use arrows, then a lot of times you're kind of just showing the grader, hey, I'm just moving this along. I'm not saying these are equal. I'm just moving. I'm just going through my progression of steps. But this is it's one of those things where it just seems like a minor thing, but just to be safe, right? Either you don't put anything in between, right? You put this here and you then put a 6, then you put a 1/3 times 6, then you put a 2 and you circle the 2. If you don't put any notation in between, that's fine as well. I think the issue comes when they see equal sign and it's connecting all these things that are not equal to each other. So this is what it is. Linkage issue is solution presented using equal signs to connect expressions that are not equal. So things like this. So either use arrows if you're trying to connect a bunch of different parts together, or just don't do anything. Just don't put any arrows or equal sign, and just show your work from one step to the next in progression and try to avoid equal signs. Now, if it's equal sign within like a line, that's usually fine because all these are just equal signs, right? But if you're just showing a bunch of equals outside from one step to the next, that's where some issues may occur. All right. Any final questions you guys have for me? I'll stick around as well if you want to ask questions, or if you want me to go over a specific problem from another review packet. I also have a last-minute packet for created number 2 and 3. If any of you guys have looked through that, or if you're looking through it now where you want me to go over any specific problem, I'll be happy to do that. Okay, but otherwise, I will send out another reminder tomorrow morning, just to make sure that you guys have your e-ticket, and that you're remembering to log in at 1:30. Checking your phones to make sure that that you have JPEG files and not HEIC format. All right, so let me see here.